maybe we can start. So, as I told you last time, we have these additional materials in the lecture folder. One of these is this 8X-Compo that describes computational units of this DSP. And last time, on last lecture, we ended with describing the barrel shifter. And barrel shifter is described on page 30 something, 35 or whatever. Barrel shifter, page 32. So you have examples of instructions, what happens after execution of particular instructions. It is the same architecture that I have described last time. We have this 16-bit input register and 32-bit output register that is composed of upper word, shift register 1, lower word, shift register 0. Each of those is 16-bit. And we have this SE register which can hold the value how many positions I want to shift left or right. So this information comes either from the instruction as immediate constant value, or it comes from this SE register that must be initialized with one instruction prior to shift operation, and after that you simply perform shift that will use this value as information how many bit positions to the left or to the right. You have here several examples what happens for arithmetic shift, for logical shift, and it describes two cases. When you have high reference, shift left or right relatively high to the upper word, or shift left or right relatively low. And in this case, the input value was ABC, blah, 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 blah. And then this value is shifted to each possible position in the output register based on the input value that is either in this SE register or as a constant in the instruction. Then it supports 128 shifts to the left or to the right. Of course, it doesn't make sense to shift something 128 times since the output register is only 32-bit wide. But nevertheless, the width of this register, SE, is 8 bits. So it is two's complement value, 8 bits. So theoretically, it supports shifting left or right by 128 position. The idea is that if you have such huge dynamics of shifting, it doesn't make much sense, but it solves exceptions. So normally you would have this range plus minus 32-bit position. But if you, for example, based on some computation, it turns out that you have to shift 50 positions, then it's not a problem. You simply write 50 into this register, and it will shift out this value to the position that is not registered, let's say. The value in the final register will be 0. So in that case, you don't have to handle this as a special case. If this shift is larger than 32 or less than minus 32, in this case, the result is 0. You simply put in the value of 50, and what happens is exactly what you desire. Okay? And then they describe two cases, whether it is arithmetic shift or logical shift. In this case, it is example how this exponent detector works. This exponent detector is the first instruction that is used to find leading number of zeros or ones based on the sign of the input value. If this input value is positive, so the first bit is 0, then this exponent detector counts how many leading zeros you have in the input register shift SE. And this value is then stored in this SA register, SE. So this SE is SI. So the SE is SI. Okay, and this SE is SA in Croatian. So it makes a bit confusing. But so in Croatian we would say SE for SI and SA for SE. So that's the reason for confusion. Then we have the actual instructions: arithmetic shift, logical shift, normalization, and derive exponent. This derive exponent is used prior to normalization. So in first instruction, let's find what is the exponent. So it counts this leading number or excess number of leading zeros or excess number of leading ones. And after this instruction, this value is written to this SE in the English register and used as a control value to shift the input value, either left or right, to normal, only right, so only left, sorry, because normalization is only left shift. And it performs left shift, arithmetic left shift. It doesn't matter whether it's arithmetic or logical if it is left shift, okay? It performs the left shift with a negated value of SE register. So this that is the reason why in this architecture you have this negate. This negate is activated only for normalization instruction. For normal shift instruction, you simply pass this SE register directly as a control input to the shifter array. But if you want to normalize the value, actually the direction is opposite of shifting. So with this X instruction, you find out what is the exponent of the shifter input value, and once you have this exponent stored in SE register, then you negate this value and use it to shift left the corresponding number of positions. So that is useful for normalization instruction. There are several examples how this exponent detection works and how it is combined with normalization instruction. There is also one special instruction that enables detection of a common exponent of several or block of numbers. So for example, you have 128 different values, and you want to find how many bit position to the left they can be shifted without causing overflow. So you want to normalize not only single value, but the whole block of values. So you are trying to find a common exponent for the whole block. And for that purpose, they have a special instruction. It is called block exponent adjust, something like that. Block exponent adjust. You simply perform this instruction in a loop for all these 1024 values. And at the end of this register, you will have the exponent, common exponent for the whole block that can be used to normalize the data, all of these 1024 values. And this particular operation is useful in implementation of fast Fourier transform. When you implement a fast Fourier transform, it is useful to always keep the data normalized, to have the data values to the leftmost position in the register. This way you avoid the round-off error of the computations. So that is the reason why this block exponent detection is a useful instruction. Then it describes immediate shift. So for example, the instruction, you initialize this shifter input register, SI, to some initial value. I have to magnify it a little bit. Shifter input is, for example, B6A3, and then you perform the shift. This is left shift. No, this is logical shift, shifter input by 5 position relatively low. So it takes this value from input register, it places it over the lower output word, and then shift by 5, it means 5 position to the left. Then we have another example. So logical shift S input by -5. In this case, but relatively high. You place the value in the upper register and then shift it 5 position to the left. So you see this 1, 0, 1, 1. I have 5 zeros and then 1, 0, 1, 0, 1, 1. And the difference between the logical shift and arithmetic shift is exactly in handling the first sign bit, because the next example shows the arithmetic shift. Arithmetic shift, again, by 5 position relatively high. So since the input value is negative, So the most significant bit is set to 1. Then this sign bit is repeated 5 times. 1, 2, 3, 4, 5. And then I have this 1, 0, 1, 1. 1, 0, 1, 1, blah, blah, blah. So the arithmetic shift keeps the sign of the input value as desired. Okay? Then you have examples of denormalization. Okay? Then you have the examples of normalization. And finally, I have this instruction, find the exponent. This exponent can be applied to shifter input register, but also to any of the result registers of other executional units. For example, you can take MR1 or whatever other register as input value, and then shift it either relatively high or low. If there is no argument by how many bit position I perform the shifting, then it means that it comes out from this SE register. So this SE holds the value. So it says here SE was prior set to -3, and then it means this instruction will perform right shift by 3 position. Sorry. No, so this is the exponent detection. Sorry, this is the exponent detection. So what I see here, I have 3 excess leading ones. So normally, if this value would be negative and normalized, I would have only 1, 0, 1, 1, blah, blah. So these 3 ones on the leftmost side are excess ones. And then with this instruction exponent of AR, I will finally have this value -3 stored in this SE register. And after negation, this value can be used for normalization. So if I use norm instruction after this one, it will simply take this -3 value, convert it to +3, and then perform shift by 3 position to the left, and you will have in 2 assembly instruction normalization of the input value. Okay? And then it describes the application of this high and low reference to perform double precision shifting. And in this case, you combine this with this OR operation. For example, I first take the input was 32 bits. So you have upper word and the lower word. And then you perform first instruction to detect the exponent of the upper word. In this case, the upper word was this. Blah, 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 blah. So again, I have 3 ones that are too many. Again, they've set this value to -3 after the execution of instruction exponent of input value that is higher upper words. After this, I apply the same instruction, but I say relatively low. And the second input was this. And what it says, I simply combine these 2 values, the upper word and lower word, as one 32-bit value. Since the leading one was already found in the upper word, this second instruction changes nothing, because already I have found in the upper word that the excess number of ones is 3. But for example, if the upper word would be all ones, that would mean that the leading one is somewhere in the lower word. And by applying this second exponent instruction, but relatively low to the lower word, you will simply get the actual value that is -17, for example. So because the leading one is in the lower word, not in the upper word, but on the 17th position of this 32-bit value. So by combining these 2 exponent instruction for the upper word and lower word, you get the final exponent of the input 32-bit value with only 2 assembly instructions. And then once you have this exponent, then you first normalize, for example, the upper word, and then use this OR operator to combine the result of the shifting of the upper word with shifting of the lower word. So for example, now I apply this -3 after negation. It means shift to the left by 3 position. So you see here this 1 0 1 1 0 1 0 1 1 0. So the 3 bits are shifted from the right side after normalization. But after that, I combine this value with OR operation and put another lower word, again shifted by 3 position. The lower word was 0 1 1 0. So it comes out here, 0 1 1 0. And then you have 3 zeros shifted from the right side in the lower word. So actually with 4 assembly instruction, you can perform exponent detection of 32-bit value and normalization of this same 32-bit value by a given detected exponent. Okay? And there are several other examples here you can check by yourself. And that is, I think, the last page describing this barrel shifter. Okay. In the actual exam, you would have examples of this kind of instruction. So if the input is this, what happens after this executing this instruction? Please write the expected result. Okay. So that is the reason that you should study this material. Okay, then I'll go further to the presentation. Finally, I will describe this multifunctional instruction that actually introduced this parallelism, this concept of parallelism that is one of the main features of this DSP architecture. So the idea is that all of this here is one assembly instruction. But what it does, it actually performs 5 different operations. One operation is multiplication with accumulation. So this is the actual arithmetic operation, multiplication with accumulation. Then it performs 2 data fetches simultaneously from data memory that is addressed by address pointer I0, fetched value, and write it to MX0 register, one of the input register of the multiplier for the left branch of the multiplier. And simultaneously perform another data fetch, but from program memory, based on address in address pointer I4, and fetch this value into input register MY0. And these 2 values are actually prepared for execution of next assembly instruction. So they are preloaded or prepared as argument for the assembly instruction that follows. So although I use the same set of registers, MX0, MY0 here in make instruction, as well as here in fetch instructions, here I will use the original value stored in these 2 registers, the old value, and the new value will be written over these 2 registers exactly at the end of execution of this instruction, exactly before the next instruction, for example, another make. So if I simply repeat this instruction, in each instruction I will prepare a pair of new arguments for the next instruction. I will use the prefetched values MX0, MY0 from previous instruction to do the multiplication and accumulation. And for that reason, I can realize one node of this FIR filter using single assembly instruction. So I have 2 fetches, I multiply the previously loaded values in make unit, I accumulate them, and also finally this comma M0, comma M4, it means update address pointer. So the I0 pointer is modified by simply adding the value stored in M0 register. So this M0 register can be, for example, initialized to 1, to +5, or to -7, whatever. So I simply initialize this modifier register with some value, and then after fetching, it is post-modify of the address pointer. So after fetching, the address pointer is modified with the value in the corresponding modification register. The same is for the I4 pointer, and these two pointers and the corresponding address generation unit will be described next. So this is just one illustration what can be done in a single assembly instruction. So although I have here 5 operations, make 2 fetches and 2 address modifications, I perform this in single cycle. Okay, and this is this address generation unit in detail. There's a separate document that describes these data address generators. There is a set of 4 registers, 4 address registers in each of those. I have DAG0 and DAG1. This one shows only one of those. For example, DAG0 or DAG1. They are called DAG1 or DAG2 or DAG0 or DAG1. Let me check. What is the original designation? 1 and 2. So data address generator 1 and 2. DAG1 and DAG2. So this DAG1 has one special feature that DAG2 does not have, and this is special block that does bit reversal of the address. I will explain later on what it means. But everything else is common for both units, for DAG1 and for DAG2. And it means each of those has 4 address registers. For DAG1, these are I0, I1, I2, I3. And for DAG2, I4, I5, I6, I7. So 4 address registers. These registers are 14-bit wide because the memory space is only 14 bits for both data memory and program memory. And these here are corresponding modifier registers. Again, 4 of those. M0, M1, 3, 4, I'm sorry, 0, 1, 2, and 3, and 4, 5, 6, and 7 for another DAG. But you are not restricted to use only M0 with I0. You can mix them. For example, I can use I0 and modify I0 with M2. I can use I3 and modify this I3 with M1, for example. You can combine independently the address register and desired modification register. That is useful if you, for example, in your application have only a given number of modification you need. Update by +1 or by +2 or update by -1, so increment by 2 or decrement by 1, then you can preload this value in these 4 registers. And only simply invoke one of those registers as a modification register after the fetch instruction. So, for example, if M0 would be -1, then if I say do the fetch with I0, comma, what I said, I don't know, M0, then it means then in this case it will decrement I0 by 1. So you simply store the desired value of modification values in this set of M register and invoke one of those registers after performing the fetch operation by simply having this comma M0. Okay? Then it says here, it is like a simple ALU. I take the current value of one of those 4 registers that is used for addressing, and I add the 14-bit value from one of those modification registers selected in the instruction. I get the result, and I write back the value into this I register that was used for addressing. But there's another block that is here described or shown. This block performs modulo operation, modulo addressing. And this modulo addressing is best described on the example. So for example, I want to address this data buffer, but not sequentially. but by incrementing by 3 position. And I want, again, I want to automatically wrap the pointer around when it comes to the end of the buffer. That is my desire, to have some kind of efficient architecture to say, okay, I start from this address 30, then I want to increment by 3 position to 33, again increment to 36, but now I have to wrap around. So it is 37, 38, 39, but this 39 is actually wrapped to 31. Then again, plus 3 is 34, plus 3 is 37. Again, I wrap around to 32. Then plus 3 is 35, and by adding again 3, I come back to 30. And I repeat the cycle, so I have this peculiar way of addressing these 8 values in the buffer by reading them on with three address values separation. And to perform this kind of addressing, it is very useful in algorithms for signal processing, as well as, for example, implementation of fast Fourier transform, such addressing. To implement this kind of addressing, you need modulus. So you need the value, what is the size of this buffer? What is this wraparound boundary, after which I have to wrap around and go to the beginning of the buffer. So to define this value, the size of the buffer, there is a special register. But in this case, L0 would directly correspond to I0 register. They are not, they cannot be mixed as I and M register, but in this case, L, for example, 3, would always correspond to register I3. And what it does, it defines what is the buffer length for register addressed with I0, for register with I1, and so on. As an example of program code, in this case, I initialize the value of this pointer to some address in the memory that will store coefficients of some FIR filter. And I say here modification value would be 2. But L3, the corresponding modulus, is 0, which means I don't want to perform modulo operation, just simple linear update. I want to deactivate this modulo logic. And to deactivate modulo logic, you simply say, okay, corresponding register L3 is equal to 0, and that means after modifying I3 with M2, it simply adds 2 to the current address, 3802 would be the new address after the fetch. But if I say, okay, L3 is not 0, but the length of the buffer that stores this coefficient, and this length of the buffer in this assembly syntax is denoted with this percent sign, the length of the buffer that begins with the address coef, and that is the first address, the initial address of the buffer. So this head is the first address of the buffer, and with modifier equal to 1, after this fetch instruction, it will take into account what is the L3. So once it reaches the end of the buffer, it will automatically wrap around to the first position of the buffer. That is useful because you don't have to do this checking in your assembly code manually. So whether the pointer reached the end of the buffer, in this case I have to reinitialize the pointer back to the first address, and all of this would be a waste of instruction, large overhead. So to avoid this large overhead, you have this hardware, dedicated hardware, that automatically checks this and performs desired modulo addressing. Okay? And there is one limitation regarding this modulo logic, and this limitation is the beginning address of the buffer. The beginning address of the buffer cannot be arbitrary, but must be divisible with the first power of 2 larger than modulus. So for example, if modulus was 6, I desire 6 position in the buffer, 0, 1, 2, 3 to 5. In this case, the first larger power of 2 is 8. And the starting address of the buffer must be divisible by 8. It cannot be, for example, in hexa 3001, 3801. It cannot be that, because this is only the second location in the buffer that starts with the address 3800. So the initial address of the buffer is always with the last given number of bits set to 0. So if the modulus is 6, then I have 3 bits that are set to 0, and this denotes the first address of the buffer. Okay? That is the only limitation in this architecture, to simplify the implementation of this modulus logic. Okay? Finally, as I said, there is an additional block that does bit reversing of the address. So it is exactly as you would flip the address left to right, each bit position. So this kind of special or weird modification of the address is useful again in implementing fast Fourier transform. Because if you have heard, there are two algorithms. One is decimation in time, the other is decimation in frequency. And to perform this decimation, how do you access these data values from the buffer, from the fast Fourier transform buffer? You actually, after performing simple increment of the pointer, then you also reverse this address pointer bit reverse. And you get exactly the address you desire based on this decimation, either in frequency or in time. And to do this on normal CPU or on some microcontroller, to do this bit reversal, you would have to perform, I don't know, 16 shift operation or rotate operation just to get this proper value mirrored, the address mirrored in the register. And this mirroring is done in hardware. So this can be activated, and after activation of this bit reversal logic, this addressing will automatically be behaving as desired for efficient implementation of fast Fourier transform, for addressing of the arguments that are read from this buffer. Okay, that is regarding these data address generators. Finally, only a few words regarding the program control of this CPU, of this DSP. What are the peculiarities of this program controller? It says here, so the next address that is used for fetching from program memory is driven by the program controller. And this next address can be simply program counter incremented by 1 as a normal sequential instruction. It can be from program stack. If you, for example, do the return from subroutine. So if you execute return from subroutine as the last instruction, then it will pop the value from the stack, write it in the program counter, and go back to the next instruction after the invocation of the subroutine. The same thing is with interrupt request servicing. So if the interrupt occurs, then this current program counter is written on some hardware stack, I will describe later on. And after servicing this interrupt service request routine, the final instruction, return from interrupt, will again pop the value from this program stack and write this value over the program counter, just to go back to the main program where this execution was interrupted by interrupt request. And finally, the value can come also from instruction register if it is some kind of jump. If it is jump, then this address where jumping or jump subroutine comes from part of the instruction register, and it is used as a new address for branching. Okay, and it says here, so program counter is used for sequential execution of instruction. Program stack is used for return from subroutine, so for return from interrupt service request, but also to jump it says here to jump on the top of do until loop. So it is one thing that is very special for this DSP. It will implement do loop in hardware. Because if you have a conventional CPU, you have some register where you have the loop counter value. And then you take this register, decrement by 1, check if it is come to 0. If not, then you jump to the top of the loop and repeat the loop until the counter is expired. All of this is done automatically in hardware. Why? Because in this type of application, usually the useful things are done in only a few assembly instructions. For example, computation of FIR filter 1 step, or maybe computation of this so-called butterfly in fast Fourier transform implementation. It takes 2 values, multiplied by some coefficient, gets another 2 values as a result. So all of these operations are done in only few assembly instructions. And if you have a large overhead, then the efficiency is low, because you have maybe 2 or 3 assembly instructions to do the actual work, arithmetic work, and then you have another 2 or 3 instructions just to control the loop. So it is then a large percentual overhead, and what you want to do is to reduce or to completely eliminate this overhead of program control, to perform the, for example, repeated do loop. Okay? And to describe this hardware implemented loop, it says here, Sklopovska izvedba petlja, so it is hardware implemented loop. It has special loop counter implemented in one of the registers of this program control architecture. And it also have the return address. So what is the top address of the loop? That once you reach the end, the last instruction in the loop, you have to go back to this instruction, to the address of the first instruction of the loop. This address is also written in some register. So you don't have to have any memory access, because everything that is done normally using some kind of stack is inefficient, because you have to fetch the data value from stack, and that is actually fetched from memory. You have to take the value from memory, and it takes at least 1 cycle to read this value from memory. But if this value is in internal register of the architecture, it can be taken from this register directly without any fetch. So you don't have this overhead of fetching the values from the stack. Okay? So I have this program stack. This program stack is hardware implemented. It has the depth of 16 words. So for example, I have 16 nested jump subroutines, one within another. It will still have the positions, free position on this hardware stack to write the return address for these 16 levels of nested jump subroutine. Okay? And of course, once you exceed these 16 values, you cannot go further, because it cannot write the 17th value in this stack, because it is limited. In this case, you have to perform some kind of instruction-based memory stack implementation to store the 17th value in the memory, and then it is less efficient, but nevertheless, this internal level of the nested loop are very fast, because they take the return value directly from this hardware stack without any fetching from the memory. And this slide here describes the execution of this do loop, or hardware supported do loop. You simply initialize this counter. It is internal register of this architecture to some value, counter equal to 10. And then perform assembly instruction, do end loop until counter expires. So this is one assembly instruction. And after this initialization of the do loop, then you have the actual assembly instructions. There can be only one instruction in the loop that is repeated a given number of times, or several instructions. In this example, you have 3 instructions within this loop. So this end loop is the address of the last instruction of the loop. And once it reaches this last instruction, it automatically decrements the counter, check whether this hardware counter has reached 0. If not, it will automatically wrap around the program counter to the first address of the do loop. To do so, it uses program stack for the return address, and it uses special loop stack to store the end loop instruction, because you might have a nested do loop. So do within the do, in this case, you have to store the counter, you have to store the last address of the loop, independently for each of the levels. So for the top level, you have one counter, one end instruction address. For internal do loop, you have another counter, another address of the last instruction, and so on. And to be able to perform this kind of nested do, then they have a special loop stack that is used to store the end loop and counter value on the loop stack, while the first address is always stored on the program stack. It is the way that is implemented in this architecture, but the idea is the following. This takes, for example, 4 cycles to initialize this do hardware. And after this, all of these 3 instructions are executed with 0 overhead. So if the number of if the number of passes is 10, then it actually performs these 3 instructions 10 times, and the number of cycles is 30, 3 times 10. So you don't have any additional overhead to control the loop. You have only 4 cycles, for example, to initialize this hardware, and after that, you simply repeat these 3 effective instructions that are used to implement the clever part of your algorithm, the arithmetic part of the algorithm, and you don't have to lose any cycle on decrementing counter, on checking whether the counter is 0, on conditional jump and everything else. And furthermore, with conditional jump, you would have also pipeline stall. As I described previously, all of these architectures are based on instruction pipeline. And if the program counter is not sequentially incremented, then the address that was fetched in this fetched part of the pipeline was the wrong instruction, because it had to branch back to the first address of the loop. And normally with conditional branch, you would have this stall. You would have to insert automatically insert wait states until the proper address is fetched finally to have the pipeline full again. But since this is implemented in hardware, it will automatically know whether it has to go up or whether it continues if it was the last instruction in the loop. So you don't have any additional no operations or wait to handle this conditional branching. So it is done without any loss in the pipeline cycles. Okay? It says here a bit about interrupts, and I will skip this because this is this instruction pipeline. Okay? It has 4 phases: fetch, decode, data, read or write, and finally execute. Okay? And if I would have conditional branching, then, for example, if this instruction sets the condition, then only after 4 cycles I would have the condition really set in the execute part of this instruction. But if the next instruction is conditional jump, it already had to fetch the next address here. And the actual condition is set here. So I actually have to wait 3 states until the condition is set, and only then I can fetch the address either from the top of the loop or as the next address. So you would have 3 cycles of stalling the pipeline. But if you have this hardware implemented do loop, it knows automatically in advance where it has to branch. What will be the next fetch address? Okay, this is more or less the last slide on this presentation. finally, it says something about serial ports, but it is not that important because these peripherals are rather archaic. So new DSPs have a little bit different peripheral ports, different serial interfaces, and of course you have to check for the current CPUs what are protocols, what are the standards that are supported with these peripheral serial units. And one of those that is commonly supported is this IIS, I2S or IIS. It is used for serial communication of audio data, 16-bit, 24-bit, or 32-bit, one channel, two channel, and so on. So this kind of high-quality stereo or high-quality multi-channel audio data is transmitted serially over such a serial bus. And you would have this serial bus and corresponding controller typically on most of those DSPs. Because in this case, they will take automatically the values from some AD converter that takes the analog value, convert it to digital value, and then serially transmit one bit by another to the DSP. And the DSP in this peripheral controller combines this bit into the word and interrupts the CPU only after the whole word is received in the input register. And by servicing this interrupt routine, you would take this word from this peripheral unit and write it into some memory buffer or directly process this data value with your algorithm. So these serial ports are already here available on this archaic DSP, but nowadays they are much more complicated than those described here. Okay. Now we'll make a break. It is 12 o'clock. And then we will skip to another presentation that describes the actual DSP that you were using on your laboratory exercises. And it is more or less similar to the architecture described here, but much more complex. So for that reason, all the examples we have to solve, all the problems in the exam are based on this very simple architecture that is described in these few documents. You can learn them. But for this Blackfin DSP that is used on the actual laboratory exercises, the actual user manual is, I don't know how many pages, 500 pages or whatever. Of course, you cannot learn this. So we take the examples from this much more similar but simple architecture. Okay. Let's have a break. Kolega je Hrvat, vi ste stranac? Sorry? You are also Erasmus student? Yeah. Okay. You are following, okay?
Yeah.
Okay.
Very much. And I was just like, because I couldn't be here for the last course, and I was looking at not the farewell page, and I couldn't find the course. Is it down on the webpage? Because I tried
The documents?
Yeah.
It is in lectures,
Yeah.
additional materials for the second part of the course. There's one zip file, lectures. So you have second part of the course, second part, repository. You have one zip, yes, one zip file. It's one zip file.
Okay.
So in this zip file, we will find this document.
And it's pretty much all equation.
Okay. This is in English.
Okay.
So these are original English documents.
sería más un día, porque es que no nos va a dar tiempo si no. Porque con lo que tardan en respondernos los correos.
Y el otro ejemplo, examen que hay de que
Esto es como la recuperación, ¿no? Parece.
nada, pues creo que está más fácil recuperación porque es toda la primera parte.
Okay. Now we'll continue with the second presentation. Okay, so in this presentation we will cover how these DSP processors are actually applied or implemented in the embedded systems that are used in practically most of the devices you have around you. We will have also the short introduction into this Blackfin family of analog devices DSP and some conclusion. So what are the advantages of DSP? So it says here they have a very simple execution core that has capable or very useful executional units which are optimized to perform this kind of signal processing operation in very efficient way. They also have very simple memory model, and typically they are based on Harvard architecture, which means they have a separate program memory space, data memory space, at least one or even two data spaces, just to be able to do the multiple fetches from these several memory spaces to have single cycle instruction execution. The instruction set and architecture are strongly optimized or customized to perform these signal processing operations. And they have excellent trade-off between the processing capabilities and power consumption. That is one of the main advantages of DSPs. With modern 32-bit RISC CPU, you can do the same thing as with DSP. There isn't any problem that you cannot do this kind of signal processing application on some ARM or whatever RISC CPU. It can be done. But if you count how many watt seconds you spend to perform the application, then you will find out that this architecture, this implementation based on some kind of common RISC or ARM architecture is energy less efficient. You would have much higher power consumption than if you do the same thing on a DSP. So that is the main difference. And of course, as soon as you have some battery-powered application like your mobile phone, then this power consumption is extremely important issue because you want to run your application as long as possible without recharging the battery. And by applying DSPs, you are able to do this in more efficient way. So everything that can be done on DSPs is at least few times more energy efficient than with conventional CPUs. And nowadays, when you have, for example, modern system-on-chip solution that is in any of your mobile phones. This system on chip would have several cores of this ARM CPU, 4 cores, 8 cores even. But beside this 4-core ARM-based architecture, they have 3 DSPs. So it is on the same silicon. They have 3 DSP processors that are implemented on the same silicon. They share the common memory space, all of these CPUs, and of course they have some kind of local memory in order to be able to execute in parallel. So each of these cores has some cache memory within the actual CPU architecture, so they don't have to go to the common memory to fetch instructional data, as long as this data access is limited to the size of this cache memory. These DSPs are then used on your mobile phone for any signal processing kind of application, and these are speech coding, video coding, image coding. So for example, if you want to talk with your colleague over the phone, conversion from your speech to the actual data bit stream that is sent over the wireless network is done with DSP, because it is architecture ideally suited for this kind of algorithm. One of the first application of DSP processors was exactly in first generation of mobile telephones. So they would have one DSP that performed this coding and decoding algorithm for speech, and another 8-bit CPU typically that was like a microcontroller to handle the whole device, user interface and configuring the system and everything else. Nowadays, you have a sophisticated operating system that is run on these ARM cores, either Android or iOS operating system. But nevertheless, part of the execution is performed on these special dedicated DSPs that are implemented on the same silicon where you have the main CPU. For example, if you take the solution from this company Qualcomm, which produces this system on chip solution for this higher quality or more expensive mobile phones, then this Qualcomm would have its own implementation of DSPs that is combined with ARM CPUs that are all implemented on the same silicon chip. And this this Qualcomm implementation of DSP it's named Hexagon. They have this Hexagon DSP, and with architecture that is quite similar to the architecture of this very simple DSP from analog devices, or to this more sophisticated one that we are introducing right now, this so-called Blackfin DSP from analog devices. Okay, so this last or semi-last was very important. So the better trade-off between the processing capabilities and power consumption. And what is also very important, they have exact and repeatable execution time. And that is very important, because if you have to implement some kind of real-time algorithm, then processing of one input sample must be done completely before the next sample occurs. You cannot spend any more time, otherwise the next sample would be discarded. This kind of real-time requirements is very critical, and for that reason the predictability, the repeatability of the execution time is very important. So each time you perform the same algorithm, the same set of instructions, the number of cycles you need to execute this part of code should be the same. In this case, you can easily predict what is the highest frequency that you are able to process in this real-time with these real-time constraints. Okay, but they have also drawbacks. So what is wrong with this DSP architecture? Typically, they have a small memory space, maybe 16-bit memory space. They also lack some instructions in instruction set that are available on CPUs for general purpose CPU. And that this fact complicates building of the whole system only based on DSP. So if you want to build the whole system, for example, a mobile phone, but only using DSP processor, it will be complicated. Why? Because if you have, for example, some operating system that is written in higher level languages like C, then compilation of this operating system into the assembly instruction on this kind of architecture, DSP architecture, is not very efficient, since it lacks some instructions that are very important to have the efficient implementation of an operating system. But again, it has instructions that are tailored to do the mathematical operation in a very efficient manner. Finally, if I want to implement compiler, it is not an easy task because, as example showed in the last presentation, you have this non-orthogonality. And that means that, for example, certain input register can be combined only with certain assembly instruction. I cannot, for example, have multiplication directly by taking, for example, shifter input value with some AX0 and directly multiply this in multiplier. Because I have to first transfer these values into this dedicated multiplier input registers, MX0, MY0, blah, 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 and only then I can implement the make instruction. So this non-orthogonality, because you cannot combine any instruction with any of the arguments, it complicates automatic compilation of your C code. And the final result is not as efficient as you would like. Okay, then as we continue, it is practically impossible to start some kind of operating system on DSP architecture like this UC Linux, because really the architecture is too limited. And this, of course, is a problem if you want to build the whole system based on DSP, especially if it has some kind of complicated or more complex peripherals like Ethernet controller, USB controller, CAN, FireWire. Because what you have to write the device drivers for all of those devices from scratch. You cannot use some kind of ready available open source solution, or maybe you can, but you have to recompile them for this architecture, and they would not execute as well as on some kind of general purpose RISC CPU. Okay. And then what are the solutions that are applied in the actual systems? It is typically based on some kind of hierarchical system that is based on two processors. One main processor, as I described, for example, in the case of this Qualcomm system on chip solution, is some commonly available or very famous ARM CPU. And then next to this main CPU, I add this DSP as an auxiliary or additional CPU to perform this number crunching, I would say, to perform efficient signal processing. All of this is done on DSP, but the operating system and the main program always runs on the main CPU that is, for example, some ARM. Okay. Finally, it is said here so the operating system and the main application is executed on the main CPU. And of course, if you select some kind of very famous or commonly used CPU, you can use many available program solutions that are either in open source domain or some that are paid. Finally, such hierarchical system is also limited in a sense that based on the performances of the main CPU, based on the performances of the DSP, but also what is the limiting factor is the bottleneck of communication between the main and the main CPU and DSP. If they have to exchange some huge amount of data, this communication bottleneck can be a very limiting factor for the really efficient implementation of the whole system. Okay, and how this interconnection can be done? It can be done by sharing a common memory space, as is typical solution on modern system-on-chip solution. Okay, there are some alternatives, some host port or FIFO buffer, first in, first out buffer, or some kind of two-way bidirectional serial communication between the main CPU and DSP over one or several serial channels, or any other possibility for communication, for connection of these two CPUs. And I will skip this. Also, what is the problem? If you want to develop a solution or program, you must have a separate team of engineers, software engineers. One team is experts for this, let's say, ARM CPU, another set of DSPs, engineers that are experts for the DSP. And of course, they must communicate with each other. They have to decide what will be done, what will be solved on the main CPU, what will be separated and solved on the DSP. And all of this is also a problem in organization, how to do it. And for this reason, since the market dedicated that in most of the application, you need some kind of hierarchical solution, like set-top boxes, satellite receivers, digital camcorders, photo cameras, digital cameras, mobile phones, PDAs, GPS, navigation devices. All of these devices had quite complicated tasks that should be implemented on the main CPU. It cannot be hand-coded in C or whatever. You have to combine everything that is available on the open source, let's say, market to have a fast and ready available final product. And maybe only develop only part that is missing. That's the idea. If you want to have some kind of fast result of your design, then you have to reuse as much as possible. Okay, these are the demands of the market. And then finally, as a solution, this company, Analog Devices, decided that it would design a special, they say, convergent DSP architecture, convergent because it would integrate some kind of common RISC architecture as well as DSP architecture in the same CPU. So not having dedicated CPU for the main processor and a dedicated CPU for the DSP, and which are communicating with some kind of inefficient communication channel that has bottlenecks. The Analog Devices decided that they would have this kind of unifying micro architecture for embedded media processing. The main application domain was obviously as shown here in this illustration for some digital cameras, from mobile phones, and so on for entertainment purposes. Okay, and of course the company Analog Devices, they had the experience in DSPs, exactly with this old CPU, old DSP21XX that we described in the last lecture. But they didn't have the experience in developing 32-bit RISC CPU. And for that reason, they cooperated with Intel. And commonly, they have designed something that is called micro-signal architecture, MSA, that combines some kind of 32-bit RISC architecture with DSP that is very much similar to the DSP of this analog devices 21XX architecture. Okay? It is a combined core. So it is not two cores executed in parallel, but actually combined core with only one instruction flow. Okay. The DSP part is based on architecture with two parallel 16-bit MAC units. So instead of having only one MAC unit, they decided, okay, we can put two multiply accumulate units on the same chip to have capabilities of performing two MAC operation in a single cycle. Okay? Then this RISC part of the core, it has all the common features that are required of a typical 32-bit microcontroller for application in embedded systems. Such combination is especially suited for application in audio, video, and communication tasks. Okay, now we come to the block scheme of the architecture of this Blackfin CPU. And what you can immediately recognize here are these two MACs. So MAC 1, MAC 2. We have these two multiply accumulate units. They are of the same width as they were with this 21XX CPU. They support multiplication of two 16-bit input values, and they get finally one 32-bit double word product. And this product can be accumulated into 40-bit accumulator A0 and A1. Since I have two multipliers, A0 and A1. Actually, it is the same 8-bit extension as we had on this described architecture. So 32-bit for result lower word and upper word, and finally for 8-bit extension, altogether 40-bit, that can be accumulated in this accumulator as well as in this accumulator. The difference is that you don't have input registers. With this simple architecture, you had this dedicated X branch and Y branch input register for the multiplier, MX01, MY01. They are absent here. I don't have them here. And what this architecture takes as input value, it comes from this register file. It is like a universal data register file composed of 8 32-bit registers, R0, R1, R2, up to R7. Each of those registers can be invoked as a one 32-bit value. If I say R0 is the argument of some instruction, or I can invoke as an argument only upper word or lower word of this register, R0.high or R0.L. In the instruction, I can select two such 32-bit registers as arguments for multipliers. For example, I can say I invoke R2 and R3, and I send them over these two buses. I have two 32-bit buses that are supplying the input arguments for both multipliers. But of course, for example, this might have left input argument R2 high and multiplied by what? By R3 low. So R2 high multiplied by R3 low is done here. At the same time, R3 high and R2 low are multiplied here. So that is the way that it can support two multiplication instruction in the same cycle, because it has two 32 buses to take actually four 16-bit values as arguments for multiplication and accumulation. It is the same as with this simple architecture. The arguments cannot come directly from the memory. So they must be prefetched into these registers with this fetch instruction. And once these are here, I can use them as an argument for multiplication or ALO operation. The ALO is also implemented here. It is not shown because it is much simpler than the multiplier. And also I have this barrel shifter that is implemented only in this first ALU, or MAC, or unit, okay, not in the second one. So it means I can perform two ALU instructions, for example, two additions, but I cannot perform two shift operations, one in one unit, another in next unit, in the second unit. I can perform only one barrel shifter operation because barrel shifter is implemented in only one of those MACs, okay?
Is it possible to mix additional
Not really, not really. This is a good question. The instruction set does not support that. So it should be either addition, subtraction, blah blah, or multiplication. Okay, but it has some kind of combination, simultaneous addition and subtraction. So the same set of arguments, for example x and y, are first added here and subtracted here. And that is useful again exactly for implementation of this butterfly in fast Fourier transform implementation, because for one branch you have to add two arguments, for another branch you have to subtract two arguments. And if you can do this in single instruction, it is the best way. I have two arguments, here they are added together, here they are subtracted, one from the other. Okay? But I cannot have multiplication in one and addition in another one. Okay? Then this part here is exactly reminiscent of the original data address generator that we had on this simple architecture. And this set of register is the same as before. I register as a pointer. L register as a modulo for the circular addressing. M register as a modification register, but it is separated from this I, L, and B because I can combine any M with any of I's. For example, I modify I1 with M2. I modify I3 with M0. Okay? But these three are commonly referenced in the sense that modulus L0 is always corresponds to pointer I0. And also what is new here, it has this base pointer. As I described previously, with this simple architecture, the base address of the buffer had to be on integer multiple of the first power of 2 greater than the modulus. So for example, if the modulus was 17, then the first larger power of 2 would be 32, and this first address of the buffer must be divisible by 32. In this case, they wanted to avoid this restriction because it complicates the linker part of the high-level compilation, and to avoid these problems how to do this efficient linking, they decided, okay, we will have a separate base register. So this B is the register that contains the first address of the buffer, okay? And then this I is always relative to this B, but modulo L, okay? In this way, I can put this buffer any place in the memory as I desire. I don't have this restriction that the first address of the buffer must be on integer multiple of this convention that is first larger power of 2 than the modulo. Okay, and this set of register is used by either DAG1 or DAG2 or both. So these registers are supplied as input arguments for this data address generator 1, but also for data address generator 0. And what they do, they generate they say two effective addresses. In the same cycle, I have two data addresses. Data address 0, data address 1, and now instead of having only 14-bit memory space, there are 32-bit. So now I have two 32-bit addresses, which are used to address the data argument in memory. Then I have a special set of address registers that are more or less copied from some kind of RISC architecture. So if you would have some 32-bit RISC core, then typically they would have this kind of 8 address registers. Some of those are special purpose. For example, stack pointer and frame pointer are used to implement the stack or to implement the frame in some higher level language implementation in C. So these two are dedicated, while the remaining registers, P1 to P5, are general purpose address registers, which can be also used to as a source of effective address. But as is shown here, they are used only with data address generator 0. They cannot be used as an argument for DAG1, only for DAG0. So this data address 0 can be generated either based on this set of address registers or with this DSP-based set of address registers. Okay? For DA1, it can be only this one. Okay? Only DSP. DAG1, DA1, only DSP registers. Okay, now that I have two effective addresses, what I do fetching from memory from these two addresses. Of course, if I have only one bus to the memory, one address bus, one data bus, and I want to do two fetches, it must be done in 2 cycles. But nevertheless, to solve this, you might have cache memory that is multi-ported, that has multiple blocks. One block for, let's say, first data space, another block of cache memory for another data space, and finally another block of cache memory for program space. In this case, this multi-ported cache can supply all 3 output values, data from the first space, data from another address, instruction from the third address in the same cycle, if they are stored in the cache. If some of those addresses is not contained in the cache, then really it must go outside to the main memory and fetch the actual value from the memory to the cache and to the core. But if you are lucky, if this address is already contained in the cache, then it is supplied directly to the core without any loss of cycles. So if it is available, I would get 2 data values from 2 addresses. And these 2 data values are coming from these 2 data buses, load 0, load 1. Okay? So these are actually memory content addressed by data address 0, data address 1. So to memory and back from memory, the content from these 2 addresses is returned to the core. And in the core, it can be only written into a register file. It cannot be used directly in executional units. It must be first written into some of the registers and then used from these registers as an argument of ALU or back instruction and so on. It says here there is a separate store data bus. It is 32 bits wide and it is only a single one, which means that in a given instruction I can store the value from some of those registers, for example R3, as a 32-bit value into memory based on address either DA0, DA1, doesn't matter, but only one store in a single cycle. I cannot have 2 stores in memory in a single cycle because I have only one bus to do the store. I have 2 buses to do the load. I can have 2 fetches from memory, but I can have only one store to the memory, and this store can be combined with load. So it doesn't have to be one load, two loads. It can be one load and one store. So for example, I load from DA0 over load bus 0, write it to register R6, and simultaneously I take R7 over store data bus and write it to DA1 into memory. So you can combine one store, one load operation, or two load operation, but you cannot combine two stores. Okay? Blah, blah, blah. It is all already said. So this block diagram shows the outside world, let's say, of this core, because only this orange part was shown on the previous slide. So this here is only this orange part, the core of the Blackfin architecture. And what is also outside of this core is the peripheral units and cache memory. So this here is this cache memory that is multi-ported in a way that I have these two data spaces, which are those, this would be L1 and L2. So two data spaces to be able to fetch two 32-bit values from memory. And if I'm lucky, if this data value is already stored in this cache, it comes directly from here. I don't have to go into outside memory, external memory. So if it is not contained in cache, then I must activate this memory interface and really fetch the data from the, for example, dynamic synchronous RAM that's connected to this chip. And this here is much slower, because this here operates on the full CPU core clock. This here takes several cycles to be able to address the data from memory, to fetch the data, and it is less efficient, especially if the access is random. So if you go to this address, to that address, to that address, if the access is random, then each of these accesses requires maybe 10 cycles just to be able to fetch this data from desired address. But if you do sequential read, it can be done in much more efficient way. You address the first address in the external memory and just say, give me sequential addresses. Okay, give me next value, give me next value, and this can be done practically at the same speed as this cache memory. So the read from memory in blocks is always more efficient than read of individual location from random addresses. Okay. And for that reason, when you have to fill in the cache with new value that is not contained in the cache, you don't read only that particular value. You read the whole block. So immediately you read the whole block because you suppose that if you needed this value from this address, probably you would also need the value from the next address, from the next address. So immediately this cache controller would fetch from the external memory the whole block of data that is contained around this location that you addressed. Okay, so this is this cache memory, the core. And finally, we have this, I would say they are like system blocks. Real-time clock, watchdog timer, DMA, so direct memory access, power management, event controller, voltage regulation, and for emulation, for debugging. And then we have peripherals, low-speed peripherals. Some can be high-speed I/O, high-speed peripherals. These peripherals are maybe shown better on another slide. The idea is some of those peripherals which have high data throughput, high data rate, they are supported with direct memory access controller in a way that automatically DMA can address these peripheral ports, do the fetching, and write the new value into memory buffer automatically without any intervention from the main CPU. So you simply program this DMA controller that immediately once a new value is available on some DMA supported peripheral, this value would be read out from the input register and automatically written into memory to the corresponding location to the address that is part of this DMA controller. So it has several channels. Each of those channels would have a counter, it would have the pointer, and simply it will take the value, write to memory to the pointer value, increment the pointer, and check whether the counter has come to the end. If it did, only then it will generate interrupt request. So only the whole block was loaded, for example, 128 data values are loaded into memory, only then you would activate the interrupt and the processor would process the whole block immediately. So this is the way to increase the efficiency. So CPU core does not have to service each particular data sample coming to these high speed peripherals. Only once I have the whole block acquired, only then I interrupt the CPU to do the processing of the block. This is useful, for example, if you have Ethernet controller or some kind of high-speed serial bus. This blocking is then a useful way to eliminate or to reduce the overhead of interrupt service request. Okay, the other peripherals that are not that data intensive with data rate, they do not support DMA. They don't need to have this DMA support, and they are typically normally handled with interrupts. Okay, only this part of the architecture works on the core clock, the full clock of the DSP. All of those below, system clock, is typically much slower. So if this would be maybe 300 megahertz, this would be 100 megahertz. So only the core part works on the full clock, and these peripherals, DMA controller, external bus interface, they always work on much slower rate on system clock. Okay. What else can we say? Let me check. It says here it has this single instruction multiple data concept. It means that in a single instruction I can perform the same operation but over a vector of input data. You have a vector A, vector B, and then, for example, you would like to add first value of A to the first value of B, and write to the first value of C. Then the second value of A, the second value of B, write to the second of C. And such concept is called single instruction multiple data, because it supports the whole vector as an input argument. So you say add this vector to this vector and write the result to this vector. And it is shown here in the architecture with these units here. So what I can do, I can actually treat these two 32-bit values as 4 8-bit values, 2 vectors. So altogether I have these 64 bits, okay? And these 64 bits can be treated as one vector of 4 times 8 bits and another vector of 4 times 8 bits. So in this case, I would like to add the first 8 bit of the first vector to the second vector, okay? And I get the result, 8-bit result for the first entry of these two vectors. Then the same thing here for the second entry of the input vectors, for the third entry, fourth entry. And now this is useful for some kind of image processing applications, because in images, the pixel values are typically represented with bytes, with 8 bits. It is sufficient to represent the grayscale level or to the value of red, green, and blue. It is sufficient to have 8-bit values for these intensities of red, green, and blue. And now if I want to add 2 images, for example, then I have to add these 8-bit values. I take one pixel from one image, the same pixel from another image, and then I add two 8-bit values together and get the result of image addition. And by having these 8-bit adders, I'm capable of performing 8 pixels at the same time. Not 4 pixels at the same time. Okay, and that is the concept of this single instruction. So the same operation, addition, but multiple data. I have a vector of 4 8-bit values here, another vector with 4 8-bit values, and I get the final result. Okay, I will stop now because it's exactly 1 o'clock. We will have another lecture tomorrow at this normal time, and that will be the last lecture. So you already had the exercise yesterday, laboratory, the 4th exercise, yeah? Was it okay?
Yes.
Okay. Then you only have to write this report for both of the exercises and submit the report by email to our assistant, Dorothea, and she will grade your result, and you'll get the points. You will see your points in this nastavni aktivnosti. So you will see the results for the laboratory exercise. If you have any question, you can also ask by email, either to me or to Dorothea.
I think that tomorrow I can't go to the lecture because I have a problem with another 2 labs and 1 presentation
Okay,
at the same time.
so all of this is recorded, and at the end I will send you the links for all of the 4 lectures.
Okay.
So they will be uploaded to YouTube, and I will give you this link to this YouTube channel, and you will have all the 4 lectures with removed breaks and everything else, so you get only the intelligent part of the lecture.